Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Earth hangs in the cosmic void as a pale blue dot, yet this seemingly fragile sphere has maintained remarkably stable temperatures for over 3 billion years. While Mars froze and Venus became a hellish furnace, our planet discovered something extraordinary. Life itself became the ultimate climate control system. The biosphere, Earth's living envelope, doesn't just respond to climate. It actively shapes and regulates it through mechanisms so sophisticated that scientists are still unraveling their complexity. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The story begins 4.5 billion years ago when Earth formed from cosmic debris. Initially, our planet's surface was molten rock under a toxic atmosphere of methane, ammonia, and carbon dioxide. The early sun was approximately 30% dimmer than today, yet somehow Earth avoided becoming a frozen wasteland. This paradox, known as the faint young sun problem, puzzled scientists until they realized that life itself had been engineering solutions. The first photosynthetic organisms emerged around 3.5 billion years ago, fundamentally altering Earth's atmospheric chemistry. These ancient cyanobacteria began converting carbon dioxide into oxygen through photosynthesis, gradually transforming our planet's atmosphere. But this wasn't just a one-way process. It was the beginning of an intricate feedback system that would regulate Earth's temperature for eons to come. Consider the remarkable stability Earth has maintained. While the sun's luminosity has increased by approximately 25% since life began, Earth's average temperature has remained within a relatively narrow range that allows liquid water to persist. This stability isn't coincidental, it's the result of countless biological processes working in concert to maintain planetary equilibrium. The biosphere operates through what scientists call biogeochemical cycles, where living organisms actively participate in the movement of elements. Like carbon, nitrogen, and sulfur through Earth systems, these cycles create feedback loops that respond to environmental changes, automatically adjusting to maintain stability. When temperatures rise, certain biological processes increase that help cool the planet. When temperatures drop, other mechanisms kick in to provide warming. One of the most profound examples involves the carbon cycle. Plants and algae remove carbon dioxide from the atmosphere during photosynthesis, effectively reducing the greenhouse effect when CO2 levels become too high. Conversely, when carbon dioxide levels drop too low, reduced plant growth means less carbon sequestration, allowing atmospheric CO2 to stabilize at levels that support continued photosynthesis. The ocean plays a crucial role in this biological thermostat. Marine organisms, from microscopic phytoplankton to massive whales, participate in vast networks of carbon cycling. Phytoplankton alone account for approximately 50% of global oxygen production, while simultaneously removing enormous quantities of carbon dioxide from the atmosphere. When these tiny organisms die, many sink to the ocean floor, effectively locking away carbon for millions of years. But the biosphere's climate regulation extends far beyond simple gas exchange. Forests influence local and regional weather patterns through transpiration, releasing water vapor that forms clouds and generates precipitation. These clouds reflect sunlight back to space, creating cooling effects that help moderate temperatures. The Amazon rainforest, for instance, generates approximately half of its own rainfall through this process, creating a self-sustaining climate system. Even soil microorganisms contribute to climate regulation. Bacteria and fungi in soil help decompose organic matter, releasing nutrients that support plant growth while also influencing how much carbon remains stored underground versus released into the atmosphere. The health of these microscopic communities directly impacts the biosphere's ability to regulate atmospheric composition. This intricate web of biological climate control represents one of the most remarkable phenomena in our solar system, a living planet that actively maintains conditions suitable for its own continued existence. The carbon cycle stands as perhaps the most critical component of Earth's biological climate control system. Unlike the simple physical processes that govern dead planets, Earth's carbon cycle pulses with life, creating a dynamic equilibrium that has kept our planet habitable for billions of years. Every breath we take, every leaf that unfurls, every microscopic organism in the ocean participates in this planetary-scale balancing act. Carbon dioxide, the primary greenhouse gas driving Earth's climate, doesn't simply accumulate in our atmosphere, as it does on Venus. Instead, it flows through an intricate network of biological processes that regulate its concentration with remarkable precision. Plants and algae capture approximately 120 billion tons of carbon dioxide annually through photosynthesis, converting it into organic compounds that form the foundation of virtually all life on Earth. This process, refined over billions of years of evolution, operates like a planetary thermostat. When atmospheric carbon dioxide levels rise, plant growth typically accelerates, a phenomenon scientists call the CO2 fertilization effect. Enhanced photosynthesis removes more carbon from the atmosphere, helping to moderate greenhouse warming. However, this response isn't unlimited. Factors like nutrient availability, water supply, and temperature constraints eventually limit how much additional carbon plants can absorb. The ocean's role in biological carbon cycling dwarfs even terrestrial forests. Marine phytoplankton, despite being invisible to the naked eye, collectively possess a biomass comparable to all land plants combined. These microscopic powerhouses absorb carbon dioxide dissolved in seawater, incorporating it into their cellular structures through photosynthesis. Their productivity depends on ocean temperature, nutrient availability, and sunlight penetration, all factors that climate change can dramatically influence. When marine organisms die, their fate determines whether carbon returns quickly to the atmosphere or remains locked away for centuries. The biological pump, one of the ocean's most important climate-regulating mechanisms, transports organic matter from surface waters to the deep sea. Larger organisms like zooplankton consume phytoplankton, then migrate to deeper waters or die and sink, carrying carbon away from contact with the atmosphere. This vertical transport of carbon creates a biological conveyor belt that helps regulate atmospheric CO2 concentrations. Scientists estimate that without the biological pump, atmospheric carbon dioxide levels would be approximately 50% higher than current concentrations, a difference that would dramatically alter Earth's climate. The efficiency of this pump depends on ocean temperature, circulation patterns, and the health of marine ecosystems. Forests represent another crucial component of the carbon cycle's biological architecture. A single mature tree can absorb 48 pounds of carbon dioxide annually, storing carbon in its wood, roots, and surrounding soil. Forest ecosystems don't just store carbon, they actively cycle it through complex food webs that determine how long carbon remains sequestered versus returning to the atmosphere through respiration and decomposition. The Amazon rainforest alone contains approximately 25% of terrestrial biodiversity and stores between 150 to 200 billion tons of carbon. This massive forest creates its own climate through transpiration, releasing water vapor that forms clouds and generates precipitation. The forest's transpiration rate responds to temperature and humidity, creating feedback mechanisms that help stabilize regional climate conditions. Soil organisms play an often overlooked role in carbon cycling. Bacteria, fungi, and other decomposers break down dead organic matter, releasing some carbon back to the atmosphere while incorporating other carbon into stable soil compounds. Healthy soils can store 3 times more carbon than the atmosphere and vegetation combined. The activity of soil microorganisms responds to temperature and moisture, creating another feedback mechanism in the global carbon cycle. Wetlands represent particularly efficient carbon storage systems. Despite covering only 6% of Earth's surface, wetlands store approximately 30% of soil carbon. The waterlogged conditions in these ecosystems slow decomposition, allowing organic matter to accumulate over thousands of years. Peat bogs, formed from partially decomposed plant material, can store carbon for millennia. The intricate connections between these biological carbon reservoirs create a planetary-scale regulatory system that has maintained Earth's climate within habitable bounds throughout most of life's history on our planet. The rise of atmospheric oxygen represents one of the most dramatic climate engineering projects in Earth's history, orchestrated entirely by living organisms. This transformation, spanning nearly 2 billion years, fundamentally altered our planet's climate system and demonstrates the biosphere's power to reshape entire planetary environments. The story of oxygen reveals how life doesn't just adapt to existing conditions, it creates the conditions necessary for its own evolution and diversification. Before oxygen-producing cyanobacteria evolved, Earth's atmosphere contained virtually no free oxygen. The early atmosphere consisted primarily of nitrogen, carbon dioxide, methane, and other gases that created a powerful greenhouse effect. Despite receiving 30% less solar energy than today, Earth maintained temperatures warm enough to support liquid water and early life forms. This delicate balance was about to face the most significant biological disruption in planetary history. Around 2.5 billion years ago, cyanobacteria began releasing oxygen as a waste product of photosynthesis. Initially, this oxygen didn't accumulate in the atmosphere. It reacted with iron dissolved in ancient oceans, creating the distinctive red-banded iron formations still visible in rocks today. For hundreds of millions of years, the oceans absorbed nearly all oxygen produced by photosynthesis, preventing its accumulation in the atmosphere. The situation changed dramatically during the Great Oxidation Event approximately 2.5 billion years ago. Ocean chemistry reached a tipping point where dissolved iron became saturated, allowing oxygen to escape into the atmosphere for the first time. This transition triggered what scientists call the oxygen catastrophe, a mass extinction event that eliminated many anaerobic organisms while paving the way for oxygen-breathing life forms. The climate implications of rising atmospheric oxygen were profound and complex. Oxygen itself isn't a greenhouse gas, but its accumulation triggered chemical reactions that dramatically altered Earth's heat balance. Rising oxygen levels reacted with atmospheric methane, a potent greenhouse gas, converting it to carbon dioxide and water vapor. Since methane traps heat approximately 28 times more effectively than carbon dioxide over a century-long time frame, this chemical transformation significantly reduced the atmosphere's greenhouse effect. The reduction in greenhouse warming, combined with the still dim early sun, plunged Earth into its longest ice age, the Huronian glaciation, lasting from approximately 2.5 billion to 2 billion years ago. Ice covered much of the planet for hundreds of millions of years, creating conditions so severe that some scientists theorize Earth may have become a snowball planet with ice extending to the equator. This dramatic cooling demonstrates how biological processes can overwhelm purely physical climate drivers. The biosphere had essentially engineered a planetary ice age by altering atmospheric chemistry. However, life didn't remain passive during this frozen period. Evolutionary processes continued, leading to more complex cellular structures and eventually multicellular organisms better adapted to oxygen-rich environments. The establishment of the oxygen-carbon cycle created new feedback mechanisms that continue to regulate Earth's climate today. Oxygen enables the complete combustion of organic matter, allowing aerobic respiration to release energy much more efficiently than anaerobic processes. This efficiency boost accelerated biological activity, increasing the rate at which organisms could process carbon and other elements crucial to climate regulation. Atmospheric oxygen also enabled the formation of the ozone layer, which absorbs harmful ultraviolet radiation from the sun. This protective shield allowed life to colonize land surfaces for the first time, expanding the biosphere's influence over climate regulation from purely marine environments to terrestrial ecosystems. Land plants could now photosynthesize without protection from water, dramatically increasing the planet's capacity for carbon dioxide absorption and oxygen production. The oxygen content of our atmosphere has fluctuated significantly throughout Earth's history, sometimes reaching concentrations above 30% compared to today's 21%. These variations correlate with major climate shifts and evolutionary events. Higher oxygen levels supported larger organisms, including massive insects during the Carboniferous period 300 million years ago, while also influencing fire frequency and forest dynamics. Modern oxygen levels represent a dynamic equilibrium, maintained by the balance between photosynthesis and respiration across all Earth's ecosystems. This balance responds to environmental changes, creating feedback loops that help stabilize atmospheric composition. The oxygen revolution demonstrates that biological climate engineering operates on timescales spanning billions of years, creating the foundation for all subsequent climate regulation mechanisms. Forests function as Earth's most sophisticated climate engineering systems, operating on scales from local weather patterns to global atmospheric circulation. These complex ecosystems don't simply respond to climate, they actively create and modify the environmental conditions that sustain them, while influencing weather patterns across continents. The intricate relationships between trees, soil, atmosphere, and wildlife represent billions of years of evolutionary fine-tuning that has produced remarkably effective climate regulation mechanisms. The Amazon rainforest exemplifies the power of forest climate engineering. This massive ecosystem spans approximately 2.1 million square miles and contains an estimated 300 billion trees. Through transpiration, these trees release roughly 20 billion tons of water vapor into the atmosphere daily, equivalent to the discharge of the Amazon River. This biological water pump creates a self-sustaining climate system that generates approximately half of the forest's own rainfall. The process begins when tree roots extract water from soil, transporting it through vascular systems to leaves, where it evaporates through microscopic pores called stomata. This transpiration process serves multiple climate functions simultaneously. The evaporation cools leaf surfaces and surrounding air, creating local temperature moderation. The water vapor rises into the atmosphere, forming clouds that reflect sunlight back to space while providing precipitation that sustains forest growth. Forest canopies create complex three-dimensional structures that manipulate airflow, temperature, and humidity. The layered architecture of tropical forests, from emergent giants reaching heights of 200 feet to understory shrubs, creates multiple microclimates within a single ecosystem. Upper canopy leaves intercept intense sunlight, protecting lower vegetation while moderating temperature fluctuations throughout the forest structure. This vertical complexity influences air circulation patterns far beyond forest boundaries. Large forests generate their own wind systems as warm air rises from sunlit canopies and cooler air flows in from surrounding areas. The Amazon's transpiration contributes to atmospheric circulation patterns that transport moisture across South America, supporting rainfall in regions hundreds of miles away from the forest itself. Forests store enormous quantities of carbon in both living biomass and soil organic matter. A single hectare of tropical rainforest can contain over 400 tons of carbon, equivalent to removing approximately 1,400 tons of carbon dioxide from the atmosphere. This storage isn't static. Forests continuously cycle carbon through growth, death, and decomposition processes that respond to environmental conditions. Forest soils represent particularly important carbon reservoirs. Decomposing leaves, branches, and root systems create rich organic layers that can extend several feet below ground. Soil microorganisms break down this organic matter at rates influenced by temperature, moisture, and nutrient availability. Cooler, wetter conditions slow decomposition, allowing more carbon to accumulate in soil, while warmer, drier conditions accelerate carbon release back to the atmosphere. The carbon storage capacity of forests responds to climate conditions through multiple feedback mechanisms. Rising atmospheric CO2 concentrations can enhance photosynthesis and forest growth, potentially increasing carbon storage. However, higher temperatures and altered precipitation patterns can stress trees, reducing their growth rates and carbon uptake capacity. Severe droughts can even transform forests from carbon sinks into carbon sources as stressed vegetation dies and decomposes. Deforestation disrupts these climate regulation mechanisms, with consequences extending far beyond the cleared areas. When forests are removed, stored carbon returns to the atmosphere through burning or decomposition of cleared vegetation. The loss of transpiration reduces local precipitation and eliminates the cooling effects of forest canopies. Regional weather patterns can shift dramatically, affecting agriculture and water resources across entire watersheds. The climate impacts of deforestation compound over time. Without forest cover, soils lose their organic matter more rapidly, releasing additional carbon while reducing the land's capacity to support forest regrowth. Cleared areas often experience higher temperatures and reduced humidity, creating conditions that inhibit natural forest regeneration. These changes can persist for decades, even if reforestation efforts are attempted. Boreal forests in northern regions play particularly important roles in global climate regulation. These vast coniferous forests store approximately 35% of global forest carbon while influencing snow cover and surface reflectivity across high latitudes. The dark green canopies absorb solar energy that would otherwise be reflected by snow-covered ground, contributing to warming effects that help maintain regional temperature patterns. Forest climate engineering operates across timescales from daily weather fluctuations to multi-century carbon cycling processes, demonstrating the biosphere's capacity to create and maintain environmental conditions suitable for continued biological activity. The world's oceans harbor the most powerful biological climate regulation systems on Earth, driven by marine life forms ranging from microscopic bacteria to massive whales. These oceanic ecosystems process vast quantities of carbon, oxygen, and heat while generating circulation patterns that distribute climate effects across the entire planet. Marine organisms have evolved intricate relationships with ocean chemistry and physics, creating feedback mechanisms that help maintain planetary temperature stability over geological timescales. Phytoplankton represent the foundation of oceanic climate regulation, despite their microscopic size. These single-celled organisms, including diatoms, coccolithophores, and dinoflagellates, collectively photosynthesize at rates comparable to all terrestrial vegetation combined. They absorb approximately 50 billion tons of carbon dioxide annually, while producing roughly half of the oxygen in Earth's atmosphere. Their populations fluctuate with ocean temperature, nutrient availability, and light penetration, creating dynamic responses to climate variations. The efficiency of marine photosynthesis depends on complex nutrient cycles driven by ocean circulation. Deep waters carry dissolved nutrients from decomposed organic matter upward through upwelling processes, while surface currents transport these nutrients horizontally across ocean basins. When nutrient-rich waters reach sunlit surface zones, phytoplankton populations explode in massive blooms visible from space, temporarily removing enormous quantities of carbon dioxide from the atmosphere. Marine food webs create biological pumps that transport carbon from surface waters to the deep ocean. Zooplankton, small crustaceans that feed on phytoplankton, migrate vertically through the water column daily. They consume carbon-rich phytoplankton near the surface at night, then descend to deeper waters during the day, releasing carbon through respiration and waste production far from atmospheric contact. This biological elevator transports billions of tons of carbon annually to depths where it remains isolated from the atmosphere for centuries. Larger marine animals contribute to carbon transport through their feeding and migration patterns. Whales consume enormous quantities of small organisms, then transport this carbon across vast distances as they migrate between feeding and breeding grounds. When whales die, their massive bodies sink to the ocean floor, carrying carbon that accumulated over decades of feeding to depths where it may remain sequestered for thousands of years. Ocean temperature regulation involves complex interactions between marine life and ocean circulation patterns. The thermohaline circulation, often called the global ocean conveyor belt, transports heat from tropical regions toward the poles while carrying cold water toward the equator. This circulation is driven partly by density differences created when marine organisms alter seawater chemistry through their metabolic processes. Calcifying organisms, including corals, mollusks, and certain types of plankton, create shells and skeletons from dissolved carbon dioxide and calcium in seawater. This process, called calcification, removes carbon from the ocean but also affects seawater pH and alkalinity. The calcification rates of marine organisms respond to ocean temperature and chemistry, creating feedback loops that influence how much carbon the ocean can absorb from the atmosphere. Coral reefs exemplify the sophisticated climate regulation capabilities of marine ecosystems. These biodiversity hotspots, built entirely by living organisms, create complex three-dimensional structures that influence local ocean circulation patterns. Coral polyps maintain symbiotic relationships with photosynthetic algae called zooxanthellae, which provide nutrients through photosynthesis while helping corals calcify more efficiently. The health of coral reefs serves as an indicator of ocean climate conditions. Rising ocean temperatures cause coral bleaching, a stress response where corals expel their symbiotic algae, losing their primary food source and their vibrant colors. Ocean acidification, caused by increasing atmospheric CO2 absorption, reduces the availability of carbonate ions that corals need for calcification, weakening their ability to build and maintain reef structures. Marine ecosystems also influence cloud formation and precipitation patterns through their effects on ocean surface properties. Certain types of marine bacteria and algae produce compounds that serve as cloud condensation nuclei, tiny particles around which water vapor condenses to form clouds. The abundance of these organisms affects cloud formation over oceans, influencing how much solar radiation reaches Earth's surface versus being reflected back to space. The seasonal cycles of marine productivity create global-scale variations in atmospheric composition. During spring and summer blooms, intense photosynthetic activity temporarily reduces atmospheric CO2 concentrations over vast ocean areas. These biological rhythms, driven by seasonal changes in light and nutrient availability, contribute to the annual fluctuations in atmospheric greenhouse gas concentrations measured at monitoring stations worldwide. Climate change is altering ocean conditions in ways that affect marine organisms' ability to regulate planetary climate, creating uncertainties about future climate stability as oceanic biological systems adapt to rapidly changing conditions. Beneath our feet lies one of Earth's most dynamic and climate-critical ecosystems, a hidden world of soil microorganisms that process more carbon, nitrogen, and other elements than all visible life combined. These microscopic communities, including bacteria, fungi, archaea, and protists, orchestrate the biogeochemical cycles that maintain atmospheric composition and regulate planetary climate. A single teaspoon of soil contains more microorganisms than there are people on Earth, each playing specific roles in the intricate chemical processes that sustain life on our planet. Soil represents the largest terrestrial carbon reservoir, storing approximately twice as much carbon as the atmosphere and all vegetation combined. This carbon exists in various forms, from fresh organic matter like fallen leaves to highly stable compounds that can persist for thousands of years. Soil microorganisms control the fate of this carbon through their decomposition activities, determining whether organic matter releases carbon dioxide back to the atmosphere or transforms into long-term soil carbon storage. The decomposition process involves complex interactions between multiple microbial species. Bacteria and fungi secrete enzymes that break down dead plant and animal tissues, releasing nutrients while consuming some carbon for their own growth and releasing the remainder as carbon dioxide through respiration. The rate of this decomposition depends on temperature, moisture, oxygen availability, and the chemical composition of the organic matter being decomposed. Temperature sensitivity of soil microbial activity creates important climate feedback mechanisms. Warmer soils generally support faster microbial metabolism, accelerating decomposition rates and increasing carbon dioxide emissions from soil. This creates a positive feedback loop where climate warming enhances soil carbon release, potentially accelerating further warming. However, the relationship isn't simple. Higher temperatures can also stimulate plant growth, potentially increasing the input of organic matter to soils. Soil moisture profoundly influences microbial climate regulation. In waterlogged conditions, oxygen becomes scarce, forcing microorganisms to use anaerobic respiration processes that produce methane instead of carbon dioxide. Methane is a much more potent greenhouse gas than carbon dioxide, so the hydrology of soils directly impacts their climate effects. Wetland soils, despite covering only a small fraction of Earth's surface, produce approximately 30% of global methane emissions through anaerobic microbial activity. Nitrogen cycling by soil microorganisms represents another crucial component of climate regulation. Certain bacteria can fix atmospheric nitrogen, converting it into ammonia that plants can absorb and use for protein synthesis. This process, called nitrogen fixation, requires substantial energy but enables plant growth in nitrogen-poor soils. Enhanced plant growth increases carbon dioxide absorption through photosynthesis, while adding more organic matter to soil carbon pools. Other soil bacteria participate in nitrification, converting ammonia to nitrites and then nitrates that plants can readily absorb. Some of these bacteria also produce nitrous oxide as a byproduct, another potent greenhouse gas that contributes to climate warming. The balance between nitrogen fixation, nitrification, and denitrification processes in soil influences both plant productivity and greenhouse gas. Emissions from terrestrial ecosystems. Mycorrhizal fungi create vast underground networks that connect plant roots across entire forests. These fungal networks transport nutrients between plants while storing substantial amounts of carbon in their hyphal structures. Some estimates suggest that mycorrhizal fungi store approximately 20% of soil carbon, making them crucial components of terrestrial carbon cycling. The fungi receive carbohydrates from their plant partners in exchange for nutrients, creating mutualistic relationships that enhance both plant growth and soil carbon storage. Permafrost soils in Arctic regions contain enormous quantities of frozen organic matter accumulated over thousands of years. These soils store approximately twice as much carbon as the entire atmosphere, locked away by permanently frozen conditions. As climate warming thaws permafrost, soil microorganisms gain access to this previously frozen organic matter, potentially releasing massive quantities of carbon dioxide and methane to the atmosphere. The composition of soil microbial communities influences their climate regulation capabilities. Different bacterial and fungal species vary in their temperature sensitivity, preferred substrates, and metabolic pathways. Changes in soil pH, nutrient availability, or moisture can shift microbial community composition, altering the rates and pathways of biogeochemical cycling. Agricultural practices significantly impact soil microbial climate regulation. Tilling disrupts fungal networks and exposes organic matter to oxidation, increasing carbon dioxide emissions. Fertilizer applications can alter microbial community composition and enhance nitrous oxide production. Cover crops and reduced tillage practices can support microbial communities that enhance soil carbon storage while reducing greenhouse gas emissions. The intricate relationships between soil microorganisms, plant communities, and climate create feedback systems that operate across multiple timescales, from daily fluctuations in microbial activity to century-scale changes in soil carbon storage. As human activities continue to alter Earth's climate system, the biological mechanisms that have regulated planetary temperature for billions of years face unprecedented challenges. The rapid pace of current climate change tests the adaptive capacity of natural climate regulation systems, while simultaneously revealing new opportunities for understanding and supporting the biosphere's remarkable regulatory capabilities. The future of biological climate regulation depends on how effectively life can adapt to changing conditions and how successfully humans can work with natural systems rather than against them. Current atmospheric carbon dioxide levels, exceeding 420 parts per million, represent the highest concentrations in over 3 million years. This rapid increase, driven primarily by fossil fuel combustion and deforestation, is overwhelming the biosphere's capacity to absorb excess carbon through existing mechanisms. While plants and algae continue removing approximately 120 billion tons of carbon dioxide annually through photosynthesis, human activities now emit nearly 40 billion tons yearly, a rate that exceeds the biosphere's current absorption capacity. Ocean acidification presents another challenge to marine climate regulation systems. As seawater absorbs excess atmospheric carbon dioxide, its pH decreases, making it more difficult for calcifying organisms like corals, mollusks, and certain plankton to build their shells and skeletons. This acidification could disrupt the biological pump that transports carbon from surface waters to the deep ocean, potentially reducing the ocean's capacity to absorb atmospheric carbon dioxide. Rising global temperatures are altering the delicate balance of biological climate regulation mechanisms. Warmer soils release carbon faster through enhanced microbial decomposition, potentially transforming some ecosystems from carbon sinks into carbon sources. Changes in precipitation patterns affect forest health and growth rates, while shifting weather patterns disrupt the timing of biological processes like flowering, migration, and reproduction that contribute to climate regulation. However, biological systems demonstrate remarkable adaptive capacity over evolutionary timescales. Some plant species are already showing increased growth rates in response to higher atmospheric carbon dioxide concentrations, a phenomenon known as the CO2 fertilization effect. Marine organisms are adapting to changing ocean chemistry through evolutionary processes that may enhance their resilience to acidification and warming. Genetic diversity within species provides the raw material for adaptation to changing climate conditions. Populations with greater genetic variation are more likely to contain individuals with traits that help them survive and reproduce under new environmental conditions. Protecting biodiversity thus becomes crucial for maintaining the adaptive potential of biological climate regulation systems. Technological advances are revealing new possibilities for supporting and enhancing natural climate regulation. Scientists are developing techniques to accelerate coral evolution, helping reef systems adapt more quickly to warming and acidifying oceans. Genetic engineering approaches could potentially enhance the carbon storage capacity of crops and forest trees, though such interventions require careful consideration of ecological consequences. Restoration efforts are expanding rapidly as societies recognize the climate regulation value of natural ecosystems. Forest restoration projects now consider not just biodiversity conservation, but also carbon sequestration and climate resilience. Wetland restoration programs acknowledge these ecosystems' roles in both carbon storage and methane regulation. Agricultural practices are evolving to support soil carbon storage while maintaining food production. Understanding of biological climate regulation is advancing through new technologies that monitor ecosystem processes at unprecedented scales and resolutions. Satellite sensors track forest productivity and ocean phytoplankton blooms globally, while environmental DNA sequencing reveals how microbial communities respond to changing conditions. This knowledge enables more effective conservation and restoration strategies. The concept of nature-based climate solutions is gaining recognition in policy discussions. These approaches work with natural processes to enhance climate regulation, while providing additional benefits like biodiversity conservation, water purification, and flood control. Examples include reforestation, wetland restoration, regenerative agriculture, and marine protected areas that allow ecosystem recovery. Success in supporting biological climate regulation requires integration across multiple scales, from protecting soil microorganisms to maintaining global ocean circulation patterns. Local actions like urban tree planting and sustainable agriculture connect to regional ecosystem management and international conservation efforts. The challenge lies in coordinating these efforts while respecting the complex interdependencies that make biological climate regulation possible. The future of Earth's climate depends largely on how well we can support the biosphere's regulatory mechanisms while reducing the human pressures that overwhelm them. This requires both rapid reductions in greenhouse gas emissions and active support for the natural systems that have maintained planetary habitability throughout Earth's history. The biosphere's 4 billion years of climate engineering experience offers hope that life will continue finding ways to maintain conditions suitable for its continued existence.